Okay, continuing with example 4.5, number 6. And in the previous video, we'd done part A. Now we're going to pick up with part B right here. And what part B asks us is find the acceleration of a car in unit vector notation and magnitude direction notation. All right, now we just found out that the change in velocity was directed in the opposite direction. All right, it changes velocity by a certain magnitude, but in the opposite direction as the initial velocity. So what we're going to find is that change in velocity is going to be very closely related to the acceleration. Because after all, we know that acceleration can be described, or average acceleration, okay, that's an average right there, as a change in velocity over change in time. All right, and very much like before when we took a displacement vector and divided it by time and got velocity, here now we can take a change in velocity and divide it by time and get acceleration. And this is going to be pretty easy in magnitude in unit vector notation, because look what we have up here. We've got that change in velocity written right out for us right here. So that is going to be negative 10.6 meters per second x hat, should be an x right there, and 22.7 meters per second in the y hat direction right here. Okay, so all we need to do is divide by this certain amount of time. How much time has elapsed right here? Delta t is, did we write that up here before? I guess we didn't. Change in time equals 0.34 seconds, right? Sorry that's so messy up there, but I would like to keep us all on the same page. So we're going to divide that boy by 0.34 seconds. 0.34 seconds. Remember, time has no direction, and so whatever direction the change in velocity is going to be, our change, our acceleration is going to be directed in that same direction as well. I should be putting arrows over these, but all right, let's just do our math now. Okay, so our average acceleration is going to be, what's that? 10.6 divided by 0.34, so that's negative 31.2. Okay, negative 31.2 what? Well, we've got meters per second, right? Or meters per second squared. Meters per second squared, that's acceleration. That's our x hat plus, x hat plus, what is it, 22.7 divided by 0.34, 66.8. All right, 66.8 meters per second squared. That's in the y hat direction right there. All right, that is going to be our unit vector expression for our acceleration. All right, look, it's slowing down, so it's being directed in the opposite direction that the car was originally moving. All right, how can we prove that? Well, let's turn that into magnitude and direction notation right there. All right, A, average velocity. What's the magnitude of this? Well, I'm not going to write it out because we're short on space, but we know that it's the square root of the x hat squared plus y hat squared. So 31.2 squared plus 66.8 squared to the 1/2 power, or that is a square root. That gives me 73.7 meters per second squared. All right, that seems pretty fast. Or pretty rapid acceleration. Okay, what is our what's our angle? So this was our magnitude. What's our direction right here? Remember, it's the inverse tangent of the y over the x. So I'm going to go second or inverse tangent of, what's the y? That is 66.8 divided by 31.2. 64.96. That's pretty darn close to 65 degrees. All right, it's all in a straight line right here. Now the question is, what direction is it operating in? Well, it's in the negative x direction and in the positive y direction, so it's going to look like that. All right, the exact same direction that our change in velocity was applied in. So that's going to be, what is it? North of west, right? North of west. So that's our average acceleration in magnitude and direction notation. The last one right here is going to be, I'll do this in green, part C, and that is the car's velocity 0.17 seconds after the driver hits the brakes. All right. So, change in velocity 0.17 seconds after the driver hits the brakes. So this is going to be interesting. In fact, we might even need a little bit more space right here because it hasn't come to a stop, but it's come to a different velocity right here. So how would we do that? Well, as it turns out, we really don't need as much space as we think we need. Remember, when we took our average velocity right here in unit vector notation and wanted to turn that into an acceleration, we just applied whatever mathematical or algebraic operation there is to it to turn that from a velocity into acceleration. So in unit vector notation, we can do the same thing as long as we know what relationships we have between what we want and what we want to get. Remember, after all, we want a change. We want to find the final velocity, all right, in unit vector notation. So it's almost like we're writing this down, writing down what we want to know. But what do we know? Okay, we know our average acceleration. Okay, we know the initial velocity, and we also know the time that is elapsed, and that is 0.17 seconds. Okay, so what we should be able to do is in unit vector notation, in the x direction and in the y direction right here, we should be able to do mathematical operations that solve for our v final. After all, we do know this, that our acceleration, oops, I'm not writing, I'm lasering, our acceleration equals our v final minus v initial, right? Our change in velocity over our change in time. Well, if we're solving for change in time, then we should move everything else to the other side. So that should mean, change in time. Sorry, we're solving for our change in velocity. Solving for change in velocity, this right here. Then that means change in velocity in unit vector notation should be average acceleration times change in time, all right, plus v initial, right, because we moved all that stuff over to the other side right there. If we simply do these math operations in unit vector form, we should be able to get the unit vector version of the v final. Okay, so how would we do that? Well, let's see here. Let's do v final up here. Hopefully I'll have enough space. We don't need as much space as we thought, but I might be able to use a little bit more space. So what is it in the x hat direction? All right, now remember, this is all in one direction. All the initial velocity and final velocity are in the and acceleration are in all the same direction. So if we take acceleration times time plus initial velocity, we should be able to get our x hat version of that. And you know what? I think it's a bad idea to write my end parentheses right there. As much as I would love to fit it in that space, I'm actually going to have to move it out here, I think. All right, sorry about that. V final is going to be equal to what? All right, well, it's going to be our acceleration. All right, so what is our acceleration x hat? Well, we wrote that up here, right? We wrote that right there, so that's negative 31.2 times what? Times the amount of time that has elapsed. That's 0.17 seconds. I'm not going to write my units in, although I probably should. All right, minus, plus what? Our v initial, right? plus, what was our initial velocity in the x hat direction? Let's go back up here and look. Our initial velocity, all right, 10.6 meters per second in the x hat direction right there. All right, 10.6. And I'll put square brackets around that. That's all x hat right there. All right. I mean, that's a big, messy thing. Yes, but it's really an equation that we know, right? V final, V initial, acceleration times time. Oh, yeah, that should sound familiar to us. So we can do these algebraic operations in x hat and y hat form. I'm obviously not going to be able to squeeze a y hat in there, so I'm going to do it on the next line, okay? So, what is the acceleration times time plus initial velocity in the y hat direction? All right, the acceleration in the y hat is what? Right here, 66.8 meters per second. Okay, 66.8 meters per second. I'll put that in a bracket. Times time, that's 0.17 seconds, plus the initial velocity in the y hat direction. That's where is that? That is up here. All right, negative 22.7 meters per second. Negative 22.7. All that. Oh, can I fit that in? I may not be able to. All this is going to be y hat right here. Y hat. Okay. Wow. That seems like a lot, but all we need is our calculators now, and we can boil this down to a very simple v final x hat and y hat value right here. And that's going to come out to v final equaling, let me get my thing here, there we go, v final equaling 5.3 meters per second in the x hat direction, all right, and negative 11.3 meters per second in the y hat direction right here. Wow, that looks big and messy, but that's really just a pretty simple way to arrive at that. Instead of going all the way back to the beginning and changing our time and all that stuff, no. All we have to do is just apply whatever operation relates what we're solving for to the other unit vector values, and we've got the value that we're looking for. All right, well, we need this v final in unit vector notation and magnitude direction notation. So how do we get our magnitude? Well, it's the square root of the x hat squared plus the y hat squared, right? So let's do that real quick. 5.3 squared plus 11.3 squared to the 1/2 power. That gives us 12.5. All right, 12.5, what? That's meters per second, right? At what direction? Well, take the inverse tangent of what over what? The y over the x, right? 11.3 divided by 5.3. And that gives us 64.9. We're going to round it up to 65 degrees. Oh, look at that. That should look familiar to us. 65 degrees, what? What direction? Well, we've got a positive x and a negative y. So, south of east. The original direction that the car was moving, because after all, the car has not come to a stop yet. It is merely slowed down. So it was moving this direction, and it's getting slower and slower, but it's still moving in the south of east direction after, well, half of the time required to stop elapses. All right, so that should make sense. Guys, the point here is, well, there's a lot of points right here, but one of the takeaways here is really to pay attention to your details. Okay, all this stuff looks messy, but it's all very logical right here. What we did here was we simply applied a kinematics formula within the brackets of an x hat and a y hat unit vector, and we came out with the answer that we should get without a lot of extra calculations and stuff. So, apologize for the extra long video this time. We're coming up on 15 minutes for parts B and C. But this is a really good example of how you can swap back and forth between different kinematics values just using unit vectors. Thanks for watching, and I'll see you next time.